Okay, I want to show you an example of graphing with the calculator and calculus. And here's the function, 0.1 x to the fifth times x plus 1 squared. And a good thing to do with this is to stop the video periodically and enter this on the calculator. I didn't want to. I'm not showing our actual calculator because I think it wouldn't come out very well in the video. So here's what the default calculator window would basically show if you did minus 10 to 10 for x and y. It just seems like it's an okay graph, and it's misleadingly nice. And that's where you can really get into trouble. It's not giving you any indication that's really horrible. The one thing that is kind of obviously bad is that you're not using any of this or any of this. It looks like it's shooting up on the y scale too fast. And so not an unreasonable thing to do is like do zoom fit or something, or change the y scale to be bigger and get something like this. And you actually have to change the y scale to be a lot bigger to get it to be nice. Because this function with those high powers of x, this blows up really quickly, even if x is only a small number between minus 10 and 10. So this looks really nice, except for one thing. It's not at all clear what's happening in here. Whenever a graph of function sort of seems to be the x-axis for a long time, you really got to wonder. And that's why I'm asking, is this the whole story? And what I want to show you is that using calculus will give us a better idea of the fact that it's not the whole story and what to look for and what interesting things it might be missing. It's really a substitute for a lot of aimless and unconfident guess and check on the calculator. You can do most of what I'm going to show you, but not all, by just changing the window a lot. But you're never going to be sure, have I really got everything? And it's going to be a lot of wasted work sometimes. So the first thing is, let's look at the limits at infinity for this thing. This thing, the definite answer that seems to be coming out of this is that as x goes to minus infinity, this is blowing up. To minus infinity, as x goes to plus infinity, this blows up. Or wait a minute, maybe it goes up and then comes back down. Maybe I'm actually missing something if I expand it out in x. Do I have to do that? You certainly could, but let's see if we don't have to do that. If you go back to the formula for the function, 0.1 x to the fifth, x plus 1 squared. Remember how to do limits at infinity for a polynomial or rational function. You just kill lower order terms. If x is really big, the plus 1 doesn't matter. So we're really getting a number, 0.1, times x to the 7th power. When x is big, that's big. And when x is big and positive, that's big and positive. When x is big and negative, that's big and negative. So that confirms that we're unlikely to be missing anything at the left and right, or top and bottom of the screen. So the big picture is probably pretty good here. It's really the small scale that we're probably missing. Second, we could look at zeros, the x-intercepts of this function. And we'll do the derivatives in a second. But if you look at the x-intercepts, that's where x equals 0 or x equals minus 1. And that already says, hey, wait a minute, that's not obvious from here. We definitely want to zoom in and try and find that. So if we just have that as our guide, that actually helps us quite a bit. And we haven't really used derivatives yet or anything, but it's already good. So here, if we zoom in a moderate amount to 0.1, minus 0.1 to 0.1. We've already zoomed in like a factor of 100. We're starting to see there's a tiny little thing happening here. Aha, we got to zoom in some more. We're going to zoom in a little bit more on x because it looks like this isn't anything new. We already know about that. And so here I'm going from minus 1.5 to 0.5 in x, and I've zoomed into 1/200th, 0.005, and minus 0.05. Now finally, aha, it looks like I've got a pretty good picture. But now we want to use calculus to really try to figure out, am I confident that that's all the wiggles? And we know how to detect wiggles in the function, at least the ups and downs. This is a local max, a local min. Here's an uphill rest. We can confirm that using calculus. And so let's go back and take the derivative. This isn't super complicated, so it's worthwhile to take it analytically. For a more complicated function, you might want to use n-deriv, which we've used, and we'll do that. We'll practice that more a little bit in class. But here, if you just use the fact that the constant comes out and use the product rule and then collect things a little bit. I factored out an x to the 4th out of both things, an x plus 1, and I collected this. You can get this result, and it's good to check yourself if you're not sure about that. And that's going to be 0 when x is 0, or minus 1, or minus 5/7. And that does seem to be confirmed by what's going on here. Minus 1, 0, and it looks like minus some fraction. Looks about right. So that's a good confirmation that it seems like we're on the right track here, and we're probably not missing anything. In particular, there are no bumps that are missing in here. We don't have to zoom in again and again and again. We know it's not going to go up and down here. We know there's no extra zeros, and we know there's not even any extra up and downs. And that's good. So it seems like that's a pretty accurate picture. Now, here's an interesting thing we could ask. Well, what about inflection points? For example, if this is like a roller coaster, if this is like a cross-section of what a roller coaster looks like, it might be interesting to know where is it steepest. Somewhere maybe in here, somewhere maybe about in here. Where is that going to happen? Well, that has to do with the second derivative. Now, we could do that purely analytically. It's a little annoying, but not too bad. We take another derivative of this. Probably the easiest way to do that is actually just multiply this out and then take a derivative, and it turns out you can factor out an 0.1x cubed again. If you try to factor this, it won't work, trust me. You could use a quadratic formula, or we could just graph that, set it equal to 0. A simpler thing might be to just plug this in as y1 and then take two n derivs. And that's essentially what would give this kind of picture. First of all, I could graph the first derivative. This is one way to answer that question about the inflection points, because first of all, it confirms the zeros of the first derivative are exactly where the 0 here corresponds to the min here. 0 here corresponds to max. And a weird kind of 0 where it just comes down and touches and doesn't cross corresponds to the uphill rest. Remember, that's about like the first derivative test. When the first derivative goes from positive to 0 to negative, that's a max. Negative to 0 to positive, that's a min. Positive to 0 to positive, that's an uphill rest. Well, we could also actually read off the inflection points off this if we wanted to. The max here, that's where the derivative of the first derivative is 0. Or in other words, in this case, it's where the first derivative is as big as it ever gets in this area. And that's where it's steepest. Well, that's going to be the inflection point. And so you could read that off, eyeball it if you wanted to. Similarly, down here, somewhere in here, I cut it off, is going to be the steepest downhill, and that's going to be maybe about 0.9 or something. There's going to be a little bit better way to do that if we graph the second derivative as well. And I didn't change the scale, so it goes off scale a little bit. But here, we see the second derivative is going through 0 at 0.9. Second derivative is going through 0 at about minus 0.53. And again right here at 0. And this is a nice confirmation. Yeah, this is an uphill rest. This is where the function is 0, the derivative is 0, and the second derivative is 0. It's a very special kind of way of crossing through the axis. And so here we've got a pretty good confirmation of all of our features. We know where the inflection points are. We know where the max, min, and this uphill rest are. We know there's really nothing else interesting about this function. And so that allows us to say, here's a good summary. Not just one graph, but both graphs. Here's the large-scale picture showing the end behavior of the function, and then the zoom in on this part, zooming in a bit in x and a lot in y. Here's that sort of micro-scale behavior. And then you can say to somebody, there's nothing else super, super interesting about this function that's hiding in here. In particular, there's nothing I could zoom in here or anywhere else and that I'm hiding. That's about the whole story. Okay.